All right, students, let's have another solution here. How about chapter 40, number 40? And it says this. It says you have a photon, so I'll put here photon, and you have an electron. So here's an electron. So you have a photon, and you have an electron. And it says here that they are equal in their energy, or the energy of the photon is equal to the kinetic energy of the electron when the electron has a speed of mu, which may be close to the speed of light. Here's what I want to start off in this problem is we have what I like to refer to as the de Broglie or the duality piece of these connections. That is, they each have a wavelength. And I like this equation because it says the wavelength, which is a wave nature, is equal to Planck's constant divided by p, which is a particle. And so it clearly shows the duality of the photon. It has both a wavelength property and a particle property. And the same thing with the electrons. And the other nice thing about them is it is the same equation for both the photon and the electron. But there's where you want to be careful. And that's my little warning to you, because the energy of the electron, which is HF, which because it is a photon and it is massless, it always travels the speed of light, so C equals wavelength times frequency. You could also write this as C over lambda, and so that's the equation for the energy of a photon. But did you notice that only works if it was traveling at the speed of light and it has no mass? So don't ever try to use that for the energy of the electron. The energy of the electron is gamma mc squared. And that is, of course, kinetic energy and rest energy. And so if you just want kinetic energy, it's gamma minus 1 mc squared. Okay? Now, of course, that would only work then when you're talking about things that have rest mass. So these are the equations for things that have rest mass, like the electrons, but this is the equation for things that have no mass. Now, there is a connection. We know that E squared is equal to mc squared plus pc squared. So you can see that whether you have mass or not makes a difference. And if you have no mass, so like the photon, you get this equation for the energy. And if you do have rest mass, then you get this equation for the energy and this one for the kinetic energy. But I think because we start talking about both of them have a dual nature, and because the equation for the wavelength is the same thing for the photon and the electron, there's a tendency for the beginning student to use that down here and saying the energy equation is the same. And this is what we call the dispersion relationship, and they are not the same. So just be forewarned about that. I've seen a lot of students go to calculate the energy of an electron using this one, wrong, or calculating the kinetic energy of a photon using this one. Now, usually they stop because they don't know what to do about the rest mass. So that's one's not so bad. But this one I see a lot, that they try to use the energy here when they're trying to figure out the energy of the electron. So that's only valid for a massless particle like a photon. Okay, so this problem, A, says that if you have a photon and then you have another particle, an electron, and they have the same energy. Now, to specify that, they have to talk about the kinetic energy of the electron. And to specify that, they have to say what speed it is. So they have a speed mu. They don't really give a number yet here. But it says calculate the ratio of the wavelength of the photon to the wavelength of the electron. Okay. So if I do something like here and I say, okay, what's the wavelength of, and I'll just put a little sub p for the photon, I would have this hc over energy, and I should put a little sub p, meaning this is the energy of the photon. However, the problem was very clear to say that the energy of the photon is the same as the kinetic energy of the electron. So I will just replace downstairs the energy of the photon with the kinetic energy of the electron. And then keep in mind then this gamma is related to the speed of the electron, and then this mass is the mass of the electron. Okay, so now if I want to do this quotient that they ask for, the wavelength of the photon compared to the wavelength of the electron. So I'll use the E for the electron. Okay, So the wavelength of the photon we just did, it's hc over gamma minus 1 mc squared. And now when I say, well, what is the wavelength of the electron, I would have this, which would be h over, and I've got p here, but let me just replace that with gamma mu. Okay. So when I go to simplify it, let's say in the numerator, I guess that c cancels off, and I could have done that back here. Oh, I guess the m is downstairs in each, the numerator and the denominator. And there's an h in the numerator. Okay, so this one here is left with nothing upstairs and a gamma minus 1c. And then this we could invert and becomes a gamma u. And they don't really say how to write this ratio, so I suppose I literally could stop there. Although, since I've done this quite a bit, watch this for a moment. If I were to factor out a gamma in the bottom, I would have 1 minus 1 over gamma c, which I know doesn't look very inviting, but it really is. Give me a second, I'll show you. The first thing is that the gammas cancel off. But the next thing is, you need to remember that gamma already is a reciprocal. So here's gamma. So it's kind of nice when you go to write things out to have things like 1 over gamma, because the reciprocal of a reciprocal is not a reciprocal, and so it's not a compound fraction. So across the top I have u, and then across the bottom here I'd have 1 minus, and remember this is the reciprocal of gamma, so up here would be the square root of 1 minus u squared over c squared. And then I still have that c floating around there. And I think that's probably the best way we could simplify it. There is a u here. I'm just wondering if we factored out a u. No, I don't see anything too inviting. So I'm gonna leave it right there. Again, we could go different paths. We could just leave it in terms of gammas back here. That wouldn't have been bad. But I'm going to put it here in U because I was looking ahead here at B. It says, now evaluate this ratio at 90% the speed of light. Okay, so the U would be a 0.9 C, which is going to end up canceling off with the C from here. And then this would be 1 minus the square root of 1 minus, and then there's the 90% of C, so the C's cancel off, so that's 0.9 squared here. And grabbing then the calculator, let me just do this one right here, the 1 minus 0.9 squared, okay. Let me take the square roots of that. Then let me go 1 minus that right there. Okay, so that's on the denominator. So if I take the numerator, which is 0.9, and divide it by that number there, I'm looking at that about a 1.60. So the wavelength of the photon is a little bit bigger. Well, 60%, so maybe I shouldn't say a little bit, but it's not hundreds of times. Okay, they're somewhat near the same value. I think if I am kind of reading ahead what the author wants, we'll come back and talk about that number here. But then let's go on here to C. C says, what would happen to the answer if the material particle, the electron, okay, were a photon. Wait, or so it was a proton. But, okay, I'm not real sure then. I thought I knew where he was going with this. But this ratio doesn't have any masses. The masses canceled off. So, nothing, I guess. Maybe that is the point. That this would be the ratio regardless of what kind of particle we're talking about. Electron, a proton, a muon, list goes on about some of these exotic particles. So, okay. So that's not real. The mass isn't important in the calculation. It could be a useful piece of information. D goes on to, it says, evaluate the ratio when we are, oh, look at that, really small. That is 0.1% of the speed of light. Okay, and now I think we can compare B and D and get to some kind of, I think the point the author wants to say in terms of electron microscope and whatnot. But now if we're going really slow compared to the speed of light, so we're not zipping along real quick. So in the numerator, I have 0.000 2 zeros and a 1. Okay. So 0.1% the speed of light. Yeah. So 001C. So there's the numerator. Maybe I'll bring this back into the screen. So I'm looking at this formula we derived in A. Okay, and then 1 minus the square roots of 1 minus 0.001 squared. C, where the C cancels off. And coming back here with the calculator again, this 1 minus, and this is going to be a really small number. So that this whole thing here is really close to 1. So when I go 1 minus that number, it's really tiny. So this top number, 0.001, divided by the bottom number, is actually really big. We're looking at 2,000 times. Okay, so what they're trying to say here is that for the same energy, okay, if you built a microscope and you put something in your microscope slide and you go to see it with visible light, photons, compared to electron microscope, then at energies low compared to the speed of light, the wavelength is 2,000 times longer for the same energy. Or put another way, electrons then, using the wavelength of an electron, so using an electron microscope, you will have wavelengths that are 2,000 times smaller. And the resolution you can see, the details you can see, are about the size of the wavelength. So, not really necessarily part of this problem, but the point of this problem is you would have a huge advantage to use electrons for viewing these microscopic things because their wavelength, for a given energy, their wavelength is 2,000 times smaller, making you be able to see 2,000 times more details with an electron microscope than with an optical microscope. That's this real point. Now, once you get, of course, to high energies, and this is what we were kind of doing back here at B, and really high energies, they're about the same wavelength. Or, put another way, electrons and photons, or electrons, become to behave almost like photons when you get them really, really fast. It makes sense. They're getting close to the speed of light. When they get close to the speed of light, their energies and wavelengths get really close to this. You can see that here, that if you're going really, really fast, it's almost entirely dominated by its kinetic energy, and there's very little rest energy. And the photon has no rest energy. And so the electron will become more and more and more and more like the photon as it gets closer to the speed of light. But in this case, D, where I'm trying to point out that it's nice that the electron at low speeds does not behave like photons. It's nice that it has this really, really, really small wavelength, but without a whole lot of energy. So you could put something under the slide, and when you illuminate it, you don't destroy it. Some things are so small that in order to see details in the optical, you have to use such a small wavelength that the energy is so powerful you destroy what you're looking at. Or even smaller wavelength, you couldn't see it with a human eye. But that doesn't mean you couldn't put up a camera. And you got to do that anyways with the electrons because the human eye doesn't see electrons. So I don't know if the camera is the big difference between using the photons and the electrons. But the real thing is we would use the electrons in order to see details without having to go to so much high energy in order to destroy them. So buried in this problem, I think, is the author's intent to try to explain the benefits of an electron microscope and how they work. All right, so off to E here. What value does the ratio of the wavelengths as you approach? So as you approach the speed of light, I kind of just said it. I'll try to prove it here, but I would be surprised if I didn't get a 1 here because as you approach, let's see, the high particle speed, as you approach the speed of light for the electrons, as I was just trying to say, you see this in the numbers that the electron behaves more and more and more and more like the photon. And the reason it doesn't behave exactly like the photon is because it has less mass. And the smaller the kinetic energy, the more the rest mass is dominating the total mass. And the more that is, the less likely it is to be like a photon. So at really high speeds, this is such an enormous number, this is almost negligible, and it acts just like a photon. I guess to prove that, we might want to jump back over and maybe skip this one, or I don't know, this one and this one. I'm just going to go this one because I know this as we get close and close to the speed of light, okay? Gamma gets closer and closer to infinity. It approaches infinity. So this bottom one, which is gamma minus 1, the minus 1 is just kind of irrelevant. You got 10 billion minus 1, forget it. So what we end up is with 10 billion over 10 billion. And then we end up with the speed u over c, which as we approach the speed of light, we approach c over c, which is 1. So I would say, yes, that's it. I guess you could see it in this one too, because again, 1 over infinity, we can go, that goes to 0, and then you've got your u over c again. And then you can actually, I guess, see it here, that if you get close to the speed of light, this is essentially 1 minus 1, that's 0. 1 minus 0 is, of course, just 1, and so you've got a u over c. So it doesn't matter which one you look at, you get a u over c. And then since u is approaching the speed of light, then the ratio would approach 1. Okay, so like I said, this is kind of our proof that the photon and the electrons kind of begin to behave the same. But again, only when you get to so high energies that the rest mass of the electron is insignificant. See, and look at F. F is at a low speed. So maybe I should have put as u approaches c. Because now we're going to say what happens as u approaches 0. Well, as u approaches 0, maybe we'll come back to this one. The gamma approaches 1, and so then gamma minus 1 is approaching infinity. Now, it may not be obvious, though, because we have this u over c here. So it might be a little bit easier maybe if I did this. Let me call u over c. The traditional symbol is beta for the ratio to the speed of light. So this would be 1 minus 1 over 1 minus beta squared as beta approaches 0. Now, this one's maybe harder to see here because I get the numerator approaching 0, but notice I also get the denominator approaching 0. And so maybe this would be a chance to do the L'Hopital's rule, and I'll take the derivative with respect to beta. So the numerator here would go to 1, and then down here, let's see, what is this? This is 1 minus beta squared to the 1/2 power. So when I take its derivative, I get a 1/2, and I get 1 minus beta squared to the negative 1/2 minus the 2 beta. Okay. I don't know if I like that much better. The 2's cancel off. So this would be 1 minus, and if I take the derivative of that, what do I get? So it becomes a plus. Okay, there's a plus. There's a beta. And then this is a downstairs 1 minus beta squared to the 1/2. Okay. So when beta approaches 0 here, I still have, no, I get a 1 over 1.